Let's take a look at the first question we had for homework, everyone. The first one was page 52, question number 2. Page 52, question number 2. Let's go over this one because we are dealing with some funny units there, the kilometers per hour thing. Okay, and I don't think that really has to mess us up all that much, but it does mess us up sometimes. So let's go over it, whether we think we need to go over it here or not. Number 2 says, on-ramps are designed so that motors can move seamlessly into highway traffic. If a car needs to increase its speed from 50 to 100 kilometers per hour, and we've talked about this a little bit, right? When we see those strange units, those things that can lead me to a silly mistake, those things that I might forget to do something with later on, I circle them in red or highlight them in pink or do something to draw attention to it. Okay, I've circled them in red so that I don't forget later on that I've got to convert that to meters per second. The engine can provide a maximum acceleration of 3.8 meters per second squared. What's the minimum length of the on-ramp? In other words, what's the displacement of the car during this time of acceleration? The on-ramp needs to be that long. So let's get the displacement of the car. Let's write down some givens here. By the way, is it a group A or is it a group B problem? Is the car going at a constant speed or is the car accelerating? I don't think that's a very hard question to answer. Group A or Group B? Both? It's a Group B problem, right? All of the ones we've been doing are Group B, right? But we don't want to just automatically go to that because every once in a while, maybe you'll get a Group A problem thrown in there. Maybe on a unit test, which is still a little ways away, maybe on a unit test, you get 3 Group B problems, and then all of a sudden we mix a Group A problem in the middle of that. Okay? Ask yourself every single time, is it Group A? Is it Group B? All right, we've got something here that's 50 kilometers per hour. We're going to have to convert that, but let's just write it down as 50 first. That's a velocity, or a speed, I should say. We'll say it's a velocity. Okay? It's a velocity in the positive direction, whatever direction that is, north, south, east, west. It's a velocity in the positive direction, and it's going to be the initial velocity, VI, because that's how fast the car is moving at the beginning of the problem, before anything's happened. We get 100 kilometers per hour here, which is going to be VF. And we got something that's 3.8 meters per second squared. Tell me what that is, please. What is it? It's the acceleration. Is it positive or is it negative? It's a positive acceleration because it's speeding up. If it was slowing down, we'd make it a negative acceleration. We want to find the minimum length of the on-ramp, so we're going to say that we're looking for delta D. I think that's all we have, isn't it? Yeah. All right. We circled those kilometers per hour in red to remind us to do the conversion, so let's do the conversion right now before we go any further. 50 kilometers per hour in meters per second is 50,000 meters over 3,600 seconds. And when you do that, I think you get something like 13.85 or something like that. Was it 13.8889? Thank you. Notice Josh, when he told me the answer there, gave it to me, I think, to 4 decimal places, 8889. We want to go to 4 or 5 decimal places, right? Let's not round it to 1 decimal place or whatever until our final answer. Keep the unrounded number as best as we can till we get to a final answer here. We're going to do the same thing here. 100 kilometers per hour to meters per second is 100,000 meters divided by 3,600 seconds, which gives me 27.77778 meters per second. Now we want to find delta D. Which of those group B equations do we want to use to find delta D? Keeping in mind, there's only one equation that we've learned that we can't try. The other ones, even if you're not sure which one to use, we can try any of them that we want to try, as long as it's from that right column, that group B column. Which one looks like it might fit the best here? Someone's got to have this. Tell me that nobody got this? That's the one that I would try as well. But let's say you tried A is equal to delta V over delta T. Well, you're not going to get delta D there if you tried A is equal to delta V over delta T, but you would get T. It's not what you're looking for, but maybe t helps you to get delta d some other way. So it's okay to try one of the other ones as long as you don't try v equals d over t. Any of the acceleration equations are valid. Try any of them. If you can pick the one that works quickest first, then so much the better. Okay, we're solving for d here. It's a bit tricky to rearrange here. Remember, we got to get rid of what is not attached first. Tell me what's not attached to the 2AD. Vi squared. So how are we going to take that over? Yes. So Vf squared minus Vi squared equals 2AD. Now, tell me what is attached to the d. The 2A, yeah. You can take them over separately, or you can take them over at the same time. I think it makes sense to take them over at the same time. How are we going to take them over, though? Yep. We're going to divide them. They're multiplied by d. Let's divide them. It becomes Vf squared minus Vi squared over 2 times A equals delta d. Now, some people, they look at this and think, oh, I've got a Vf squared. I've got to square root something. No, you don't. You only square root something if you're solving for Vf or Vi. You only square root something if you've got to get rid of the square. Okay, so don't make the question harder than it has to be, okay? Solving for delta d, plug our numbers in here now. Vf is 27.7778 minus 13.8889 squared divided by 2 times 3.8. I can't tell you how many people I saw do this yesterday. There was at least, I think, 4 of you that did this yesterday. Call me over when you're working on this in scheduled help, asking a question, which is great, by the way. Okay, if you can't get an answer, if you're struggling with something, that's exactly what you should do, is call me over and ask me the question. But how many people rearrange this properly, just forgot to square Vf and Vi? They just put it in as Vf minus Vi over 2A. How many people forgot to square? Quite a few. Okay, quite a few. You weren't alone. And then there was a couple people that actually tried square rooting them because they thought, oh, it's a square, I got to square root. No, you don't. Okay, unless you have to solve for Vf or Vi, we're not going to square root it. All right, when we do that math, let's do it on our calculator here just so that we can make sure that we can all do it here. Let's say 27.7778. Let's square that. Let's subtract 13.88889. Square that. Let's press equals now. Let's get a number on the top. And then let's divide that by, see some brackets on the bottom, 2 times 3.8. We end up getting 76 meters. Sorry, say that again? You're good, though? Okay. So it works out to be 76 meters. Good? We okay with that? All right. 1 to 10 here, 1 to 9, I should say. Which of these questions would you like to go over here now? Guys? 5, yeah? Others? Number 5, 8, 7, 5, 7, 8. Going once. Any others? Going twice. 9, 5, 7, 8, 9. Going twice. Sold at 5, 7, 8, 9. All right, number 5 says some aircraft are capable of accelerations of magnitude 42.5 meters per second squared. If the aircraft starts from rest, how long will it take the aircraft to travel down a 2.6 kilometer runway if it's accelerating at 42.5 meters per second squared? That's a pretty big rate of acceleration. That's about 4.3-ish Gs. You ever heard of a G-force? This many, you pull this many Gs as you go around a turn or something. That's 1 G is gravity. If you experience 2 Gs, then we say that you feel twice as heavy as you really are. The force acting on you is twice as much as your actual weight. If you have 4.3 Gs, then the force acting on you is 4.3 times what your actual weight is. So if you're accelerating in a plane at 4.3 Gs, you feel like you're being pushed back into that seat really, really hard. If you weigh 150 pounds, you feel like you're being pushed back into that seat with about 640 pounds. Okay, that's a lot of force. Okay. I know that the first time I ever traveled on an airplane, I was a teenager, actually, the first time I ever traveled on a plane. And I remember I was by myself. My parents weren't with me. I was in Toronto, and I remember taxiing out for the longest time, and then we turned the runway. And as soon as you turn the runway, you know how they gun it as soon as you turn out onto the runway. And I thought, holy cow, this is like, it's pushed back in my seat. I could barely lift my head off the seat. It is a lot of force. I would say that it's probably not 4.3 Gs, usually, because if it was, there's no way you'd be pinned against that seat so hard with 600 pounds of force that you'd never be able to lift your head off. This is a lot of force, but this would be something like maybe a fighter plane or something like that, which experience more acceleration than, say, a commercial aircraft do. All right, we got some numbers here, and we have one non-standard unit there, so we're going to circle it just to make sure that we don't mess up on that. What's the 42.5 here? Is that V? Is that VI? Is that VF? It's acceleration. It's none of the above. Good. It's acceleration, and it's positive because it's speeding up. The aircraft starts from rest, so VI will be, yep, good, 0 meters per second. We don't know what VF is, but we do know that something is 2.6 kilometers, which in just a minute we're going to convert to meters. 2.6 kilometers, what is that? Displacement, good. Let's convert that to meters now. What's the conversion factor from kilometers to meters? Right, so it becomes 2,600 meters. What is it that we want to find here? How long will it take? We're looking for the time here. Okay, group A or group B? I think it's pretty clear here, right? We're given the value of the acceleration. I think it's pretty clear that it's a group B problem. Which one of our group B equations should I try? Any of them are okay to try, right? You can't go wrong by choosing any of them. It just means that sometimes you might have to try something else. You might not have enough to use one of the equations. Fraser, which one do you want to try? Okay. That one's perfectly valid, so let's write that one down and give it a shot. Now, I will caution you, if VI wasn't 0, T, you're not going to know how to solve for T. Okay, if VI has a value other than 0, you can't solve for T without the quadratic equation, which only one of you knows. If VI is 0, then that makes this dramatically easier mathematically to solve. So we can try it. By the way, I'll never give you a problem where you need the quadratic equation. If you want to use it sometime, you go ahead. But I'm never going to give you a problem where you need it, because you guys haven't learned it in math class yet. All right, I'm crossing that off. How come? VI is 0. Now I want to solve for T. D is equal to 1/2 AT squared, solve for T. I'm going to get rid of the 1/2 and the A. I'm going to get rid of those by dividing. How come? Why did I divide by 1/2 A? 1/2 and A are multiplied by T squared, so we get rid of them by dividing. How do I get rid of the squared? This time I've got to do it, right? This time I've got to square root it, because I'm solving for the something that is squared. That last question, we didn't have to do that. All right. Delta D is 2,600. divided by 1/2 of 42.5. We square root that. Let's put those into our calculator as well. See what we get? Let's go inside the brackets first. 2600 divided by, or inside the square root sign first, divided by 0.5 times 42.5. Okay, inside the square root sign, that gives me 122. Let's square root that now. Becomes 11 meters per second. Or 11 seconds, I should say. So this plane is starting at rest and traveling down a 2.6 kilometer runway in a grand total of 11 seconds. Ooh. Sure. There's almost always another way to do that. Who said that? Okay. There's almost always another way to do it. How did you do it? Yeah. 2AD, yeah. Okay, which is a perfectly valid equation. Just hold on there 1 second. Okay, we've got A, we've got D, we've got VI. That allows us to solve for VF, even though it's not what we're looking for. It's okay. It's a perfectly valid thing to solve for. Then we can use VF in another equation to solve for T there. Which one did you use after that? Okay, good. The way that I did it is slightly quicker because it's only one equation, but I'd never say that it's better. Okay, your way is correct, which means it's just as good as my way. Okay. What did you get, by the way, for the final speed? 470.10. I was going to say, I don't think it's going to be a realistic final speed. If you're traveling down this runway in 11 seconds, 470 meters per second is about 1.5 times the speed of sound. There are airplanes that can go faster than the speed of sound, but not when they're taking off. They beat the speed of sound as they're over the ocean somewhere and they've been flying for a while. Not when they're taking off. So, the method is good. Okay, doesn't matter which way you do it. Let's take a look at number 7 now. It says, approaching a flashing pedestrian activated traffic light, driver must slow down to a speed of 30 kilometers per hour. We keep seeing that, right? We keep seeing that kilometers per hour thing, which was okay when it was constant speed, but not anymore. We've got to be in meters per second now. If the crosswalk is 150 meters away and the vehicle's initial speed is 50 kilometers per hour, what must be the magnitude of the car's acceleration to reach the speed limit? I got a quick question for you before we write down any givens or solve anything. What do you know about this acceleration right now? Before we actually get a number for it, what do you know about it? What should we expect to see once we've calculated the value of our acceleration? Aiden? Yeah, it should be a negative acceleration, deceleration. So we should be prepared to see that. If we don't see a negative acceleration, it means we've done something wrong. All right? 30 kilometers per hour, what is that? The velocity, right? But V what? V initial, V final, V, just V? Rutger? Yes, it's the final velocity. It's how fast you got to be moving before you get to the crosswalk. That must mean that 50 is VI. We're going to say the displacement of the car during this time is 150 meters away. And we're looking for the acceleration. Is that all? I think that's it. Which one do you want to try? Hey, let's convert these actually first. 30,000 meters over 3,600 seconds is 5, 6 feet. Is that going to be 8.33? 8.3333? And this is going to be, was it 18.88889? Yeah. Oh, 13, yeah. Yeah, right. We do that the same way, right? We multiply by 1,000, divide by 3,600. Okay, which of our group B equations, it is clearly a group B problem, which of our group B equations are we going to try here? Come on, you guys. Cassidy, what do you want to do here? Yeah, that's exactly what I would do as well. Is there anybody else that tried something different? Yes, what did you do? Okay, so d is equal to vi plus vf over 2 times t. You would have solved for t there, and then that would have helped you to use another equation to solve for a. Probably a is equal to delta v over delta t at that point. Perfectly valid, but this is only one equation. This allows us to only use one. So it's a little bit quicker, more efficient, but no more correct. Yes? vi squared, yes, thank you. All right, so we're solving for a here. Let's get rid of the vi squared first because it's not attached. We take it over by subtracting. Vf squared minus vi squared equals 2ad. And then we got to get rid of the 2 and the d by dividing. Becomes vf squared minus vi squared over 2 times d equals a. Okay, now it's not so tough. Just remember a couple of things. One, when you plug in your numbers for VF and VI, make sure you square them. Okay, make sure you go 8.33 squared minus 13.8889 squared. Secondly, make sure that when you calculate that top number, 8.33 squared minus 13.8 squared, make sure you press equals on your calculator. Get a number on the top. And then divide it by 2 times 150. Get that number. Divide it by, notice I got a negative number on the top. Divide it by 2 times 150. Gives me negative 0.41, which is exactly what Aiden told me that I should have when I get a final answer here. What was that, 0.41? Yeah. Good? Okay. Let's try number 8. Train stopping distance even when full. Brakes are engaged is 1.3 kilometers. That doesn't tell us much. Must have been more to it. Let's go back. We had another part there. That's better. If the train was traveling at an initial velocity of 90 kilometers per hour forward, determine the acceleration in order or under full emergency braking. The stopping displacement here is 1.3 kilometers, which we're going to want to convert to meters. We've got an initial velocity of 90 kilometers per hour, a final velocity of 0 because it comes to a stop, and we're looking for the acceleration here. (1,300 meters). 90 times 1,000 divided by 3,600 is 25 meters per second. What about this one now? Somebody knows the answer to this one, so get off the hook. Raise your hand and get off the hook here before I call on you on one you don't know the answer to. Hayden helps me out lots too, but not quite as much as you. Hayden, what's the equation you want to use there? Good. Again, right, we use that quite often here, right? And we're solving for A, which is, I think, what we had to solve for the last time. So we do it the same way. VF squared minus VI squared over 2 times d equals a. Plug in your numbers, do your thing, we get a value for a. Does anybody have the answer for that? What do we end up getting for a there? Negative 0.24 meters per second squared. So trains do take a while to stop. I'm not sure about 1.3 kilometers under full emergency braking, but in the end they do take a big distance to stop. Why would they take a long distance to stop? Why do they take so far to stop? Well, they're heavy. You're going to learn about something next unit called inertia. Inertia is related to mass. The more mass something has, the harder it is to change its motion. These guys give a lot of inertia. It's hard to stop them. I remember a few years ago I was driving downtown beside where the town office is now. It was Scotiabank at the time, and where our school board office was the Royal Bank at the time. And I remember I stopped there with my wife to get some money at the Royal Bank so we could go home and pay the babysitter that was babysitting the one son that I had at the time. And so we stopped there and run out and get some money, and then I get in the car, and then I pull up to the train tracks as I was going to go around, and I realized, there's a train coming. So I decided to take a ride, to drive down behind the town office in that little alleyway, and then come out another way. So when I do that, I stop at the hi-ho there to get some change, and I come back, and I notice the train has stopped on the crossing now. I never heard it stop, but stopped on the crossing. And so I drive up to it, and I realize the train has stopped on the crossing because the van that was behind me in line to cross the tracks, when I turned right to go down that alleyway, decided that he was going to try to beat the train, and he didn't. And he didn't beat the train. He got hit by the train, literally right behind me in my rearview mirror as I didn't see it. But the point that I want to make here is that the train probably slammed on the brakes as it saw this van on the track, and then it hit the van, and then of course the emergency brakes would still be on, and it was still almost 400 meters down the track that this van was. The train carried this van 400 meters down the track, even after putting the emergency brakes on the train before it hit the van, and then obviously after it hit the van as well. Okay, trains have a lot of inertia. It takes them a long distance to stop. Yep. Well, I read in the paper that he ended up being okay with relatively minor injuries, actually. But by the time I was there, there was lots of people there already, so I didn't stop, obviously. But okay, we had one more, I think. It was number 9. Yeah. The rocket sets some rest and accelerates uniformly for 2 seconds over a displacement of 150 meters. What's the rocket's acceleration? VI is 0. T is 2 seconds. Displacement is 150. And we want to find A, right? We want to find A. Who's going to tell me which equation that we're going to try this time? Wilson says delta D is equal to VI T. Good. VIT plus 1/2 AT squared. Valid equation, guys? Sure, it's a group B problem. Any of the group B equations are valid. Now, we can solve for acceleration here. It's a little bit tricky, but it becomes a little bit simpler if I get rid of that. Why can I get rid of that? VI has a value of what? If VI is 0, then I can cross that off because 0 times time is always going to be 0. Let's take the 1/2 t squared over by dividing. I don't have to square root anything because I'm not solving for t. Looks something like this. It's 150 divided by 1/2 of 2, which means my answer is going to be 150 divided by 1, which is 150 meters per second squared. Make sense? Remember we said 42 meters per second squared was about 4.3 Gs? Is that right? What's wrong? Oh, it is, yeah, 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 it's right, thank you. So it becomes 1/2 of 4, or 2, so it becomes 75, right? 3 digits, if we look back to our data here. That's still a big rate of acceleration, but better. Okay, that's still about 7.5 Gs. So if you weigh 150 pounds, let's say you weigh 200 pounds, you're still going to feel about 1,500 pounds, which is a lot of force acting on you, 1,500 pounds. All right? Good. All right, I want you to do now page 53, number 10 to 14. So the remainder of the ones on that page. I'm going to give you just a couple of minutes right now to work on them at your desk so that I can take a walk around and give you a hand if you're struggling with it. But I'm not going to give you time to solve all 4 of these questions. Page 53, number 11 to 14, please. All right, let's take a look at one more example on this topic here right now. A little bit more of a challenging example here. It says a 1,600 kilogram car begins at rest at a stop sign, then accelerates for 4 meters per second squared for 5 seconds. The car then travels at a constant speed for 34 seconds, then slows to a stop in 8 seconds. How far has the car traveled? Now, what kind of strategy do we follow in this question? The first thing that we got to spot is that this is really more than one question. This is really 3 questions. I can't ask you, is this group A or is this group B? Because it's both. It's accelerating, and then it's traveling at a constant speed, and then it's decelerating. So there's a group B, then there's a group A, then there's a group B. We need to break this problem down into 3 sub-problems, 3 smaller problems. So let's break it up into 3 sets of givens. We'll say for problem 1, the mass is 1,600 kilograms, although as Rutgers said, the mass is irrelevant here. So whether you write that down or not doesn't really matter. It begins at rest. We'll say that VI is 0 meters per second. It begins at rest. A is 4.0 meters per second squared, and the time is 5.0 seconds. That's all we know. We're not going to put anything else in like 34 seconds or 8 seconds because that's another problem. It's accelerating for 5 seconds, and then, okay, the word then is important, and then it does something else. Then it travels at a constant speed for 34 seconds. At what constant speed? We don't know. Not yet, anyways. And then it comes to a stop in 8 seconds. So we're going to say in stage 3, something else happens in 8 seconds. We're going to say that VF in stage 3 is 0 meters per second because it does say it comes to a stop. Now, if we want to find out how far the car has traveled in total, let's find out how far the car has traveled in stage 1, then stage 2, then stage 3, and then let's add them up. Okay, stage 1 isn't so hard. Stage 1, we're probably going to say D is equal to VIT plus 1/2 AT squared. It's a group B problem because it involves acceleration, so let's use one of my group B equations. This one seems to make the most sense to me. VI is 0, so we can cross that off. It becomes 1/2 of 4 times 5 squared. That gives me a total displacement of 50 meters in stage 1. Now I've got to find the displacement in stage 2. Stage 2 is what kind of problem, group A or group B? Group A, good. It's been a while since we've done one of those group A problems, right? But it's a constant velocity. So we know it's a group A problem, and in fact, we know there's only one equation that I can use. V is equal to delta D over delta T. There are no others. It's the only one that I'm allowed to use for a group A problem. Now, I want to find the displacement, so I'm going to rearrange it to solve for delta D. Right, Nick? To do that, I'm going to take the t up by multiplying. Becomes v times t. But my problem here is that I don't know what v is. What is the constant velocity? It's great to know to use that equation, but if I don't know what v is, how do I use it? Anybody have any ideas? Good, excellent. We're going to find the final speed, actually, because of the equation we're going to use. It's going to be the final speed, but close enough, after the first stage. And we're going to do that during the first stage. We're allowed to use any equation we want within group B in that first stage, including VF squared is equal to VI squared plus 2AD. Now, some of you are going to look at that and say, well, why do we want to use that? I've already found delta D for my first stage. Why do I want to use it here? It's because I want VF. That's why. VI is 0. VF becomes the square root of 2 times 4.0 times the displacement of 50 meters. So 2 times 4 is 8 times 50 is 400. Square root of 400 is 20. Is that right? And the displacement was 50. So what did I say that was? 8 times 50 is 400. 20 meters per second, I think. If at the end of stage A it's going at 20 meters per second, then it's going at 20 meters per second for all of stage B. Let's multiply that by the time of 34 seconds. 20 times 34 is going to be 680, I think. All right, good. I got two different displacements now, stage A and stage B. Looks easy now. Let's go to stage C. You want to find the displacement here? Let's say, what do you want to do here? You've only got T and VF. Or is there something else I have if I read between the lines? Is there something else that I know in stage C and stage 3? Good. If it was moving at 20 at the end of stage 1 and for all of stage 2, then it's got to be moving at 20 at the beginning of stage 3. So we know what VI is. VI is 20 meters per second. Now, I think it makes sense probably to use this equation here now. VI plus VF over 2 times T. So it becomes 20 plus 0 over 2 times the time of 8 seconds. Gives me 10 times 8 is 80. Now we want to find that total displacement. What are we going to do? Add them up. 50 plus 680 is 730, 810. That makes sense to people? That's a great question because it combines everything. It's basically everything we've done this year, right, in that one question, except for position time graphs. Speaking of position time graphs, wouldn't it be neat if we could plot a position time graph for this whole question? Let's do that. Let's put everything that we've done this year into this question. Let's plot, just sketch. Okay, we're just going to sketch it. A position time graph for this data here. Okay, let's look at our time intervals here. First of all, we're going for 5 seconds. 5 seconds. And then we're going for 34 more seconds, so it's going to be 39 seconds, and then 8 seconds is 47 seconds. So those are going to be my relevant times. We're starting off at 0. How far are we going? Looks like 50 meters. Running out of space here. Let's do that. Let's do it down here where we have some more space. What do we say it was? 5 seconds, 39 meters, and what was it, 80? No, sorry. What do we say, 5 seconds, 39 seconds, and 47 seconds? Well, it is 34 seconds, but it's 34 seconds after the 5 seconds, right? Okay, so the first one went from 0 meters all the way up to 50 meters. So on our y-axis here, we're going to have 50 meters. And then what happened? Oh, wait a second. Is that right? What's wrong with that, Hayden?
Not curved.
Good. Its acceleration shows it should be curved, right? So it should look like this to 50 meters. Okay, then what? Then it's going at a constant speed, so now it's going to be a straight line up to 39 seconds and up to a time, a position of 730 meters. Why 730 or not? Why not 680? Because it's gone 680 past 50 meters, right? And then finally, it goes another 80 meters as it slows down. What's that mean? Is it going to go down here? Is that right? No, it's not going backwards, is it? It's just slowing down. So it's going to look something like this, right? Does that make sense? And this one is going to be, we went another 80 meters, so it's going to be 810. Is that right? What a great question that would be for a test, wouldn't it? Wouldn't that be a great question for a test? Like so far, what are we? It's September 10th right now. We've been in school since the end of August, and we've just done one question that covers every single thing that we've done this year, including Group A, including Group B a couple of times, and including our graphs. That's a great, great question. Man, I'm not going to be here tomorrow, but if I was, man, what a good question to put on a quiz. I won't do it because I'm not going to be here, but man, it'd be a great question if I was. Okay, just looking at the time here. It's 11:21. How many people, where are we at on those check and reflect questions? What question are people on here? Just looking at the clock here, guys. Just finish up these questions here today. We won't start anything new until tomorrow, okay?